Welcome back, children. We are going to look at some more related rates examples. So this is a pretty big section of calculus, but it does require us to do some planning, but the more you do it, the more rote it will become. It's not as creative as trig identities, but it's certainly got more creativity to it than just basic derivative rules. So related rate problems continued. All right. Alrighty. So what are we going to do? How about, let's think about maybe water draining out of a Dixie cup. So imagine that we had an inverted conical Dixie cup. And I'm going to tell you that the dimensions of this Dixie cup are going to be, how about we make it, 10 centimeters in diameter, and it will have a height of, make it, 15 centimeters as its height. And it's full of water currently, right? So that's a horrible representation. It's pretty close to being full of water, but it's leaking. So we got drips of water pouring out of the base of our Dixie cup. How do we want to make that blue just for fun? Is that blue? Let's pretend that it's blue. I think it's blue. Okay, so we've got water pouring out of our Dixie cup. Now, we know that the rate that it's coming out of our Dixie cup is water is leaking at, how about 5 centimeters cubed per minute. So not extremely fast, but it is leaking out. My question is, at what rate is the, how about the diameter of the surface of the water changing when the depth is, how about we make when the depth is 10 centimeters deep? Or how about we make it 6 centimeters deep? We've used 10 somewhere else and I want to get confused. How about when the water is 6 centimeters deep? So when the water gets down to, roughly this depth here, so it's going to be depth of 6 centimeters, I want to know at what rate is the diameter changing. So let's list our givens and our wants. So we are given, well, we're given that there's a ratio of height to diameter and similarly height to radius. So if we said height to diameter, it is 15 to 10. And height to radius is, well, I guess it's still going to be 15, but now the radius is just going to be 5. And why that's relevant is because this is going to form similar triangles regardless of where you have your depth. So the whole thing has a ratio of 2 to 3. Down here, it would also have a ratio of 2 to 3. Okay, so the reason I changed this to be 6 to be nice is that we could actually say, using that same logic, that when the depth here is 6, we know the diameter is 4 centimeters. But here's where it gets interesting. It says at what rate is the diameter changing? We solve for the diameter. If it was just simply a grade 10 problem, it would have been just tell me what the diameter is. But this is a grade 12 problem, so it's at what rate is that thing changing? Okay, so we know all those ratios, and we're also given that the volume is changing. So that means that dV by dt, well, it's decreasing, so I'm going to have to be sure to include my negative, and it's decreasing at 5 cubic centimeters per minute, so negative 5 centimeters cubed per minute. Okay, I also happen to know that the volume of a cone is equal to pi r squared h over 3. Now, when it comes to the test, I always feel terrible that I have to give these things to you, but anything outside of a rectangular prism, and I'm not giving you the rectangular prism, I'll give you the other formulas. So I would provide for you what the volume formula for a cone was. And what are we trying to find? Or what are our wants? Well, what we want is we want to know the rate of change of diameter. And I've chosen poorly again. Anyways, so that's what I want is dd by dt. That's what I'm after, okay? So I want dd by dt. Now, in theory, I could also say, well, I know that diameter is equal to 2 radiuses. And I could take and I could rearrange this and say that means radius is equal to diameter over 2. And I could come up into this formula and substitute that in here. And that would be perfectly appropriate, although a bit more complex than what I need it to be. So I'm going to have an intermediate step. So with experience, I know that I want an intermediate step of, I would like to know, not stem, step. I want to know what dr by dt is. And the reason I want to know that is because if I know what dr by dt is, I can solve for dd by dt, right? Because I have diameter, I'm going to use uppercase here, diameter is equal to 2r. So that means if I differentiated this with respect to time, it would be dd by dt is equal to 2 dr by dt. So if I can find out what dr by dt is, I can substitute it in right there, just double it, and it's going to end up telling me what dd by dt is. So I look at this and I think, are any of these things static? So is radius static? As this problem progresses, the radius is going to change. How about the height? Well, the height is in a similar boat. As the diameter or as the depth lowers, obviously the height of the cone is going to get smaller as well. So there's no static values that I can substitute in. So I'm going to need to differentiate this. So I'm going to just rewrite this a little bit. I'm going to say that this is pi by 3 r squared h. Same thing, just written in a little bit easier to palette form. So that's what the volume is. So I know that I'm going to have to use a product rule. I'm going to treat that as my first, and that is my second. So here I go. I'm going to differentiate. We're going to have dv by dt is equal to, so the derivative of the first, well, that's going to be 2 pi by 3r. And I differentiated r with respect to time, so dr by dt. So this is all this. So there is the first. This is the derivative of the first. And then I'm going to have to go back. And so the derivative of the first times the second. Well, the second is h. And then I'm going to say plus the first. Well, the first is pi by 3r squared times the derivative of the second. Well, the derivative of h is 1. So then it's just going to be dh by dt. And so this is not what I was after. So I realize that I've made, a relatively challenging mistake here. And I get down to this position and I think, uh-oh, I've got a dr by dt, I've got a dh by dt, and there is going to be a relation. But I, in retrospect, realize, I probably should have done this differently. So this is where, kind of having thought about it ahead of time, I would have realized, oh, there's a ratio between height and radius. So I could do some more, heavy-duty calculus down in here, and I have the capability to do it, and some of you in the class would have the capability to do it as well. But we would be better served because there is a fixed ratio between radius and height. I see that height is equal to triple the radius. And I should have spotted that earlier. So I'm going to come back here and I'm going to revisit this. So my apologies. But, it was a learning experience for you and me. So we're going to say then that volume is equal to pi by 3 r squared. And I know for this particular example that height is equal to 3 times the radius. So I'm going to substitute that in 3r on. We had this one before, similar one. Nevertheless, we're going to do this. And we're going to have that this is going to be pi times r cubed. Okay, so pi times r cubed, that's what my volume is. So all of a sudden, this becomes a little bit easier to differentiate. So let's go ahead and we'll do that. We're going to say dv by dt is going to be 3 pi r squared dr by dt. Now, we know what dv by dt is. It is negative 5. So we're going to say, all right, well, that's negative 5 is equal to 3 pi. Well, what we don't have currently yet is we don't have what the snapshot calculation for radius is. So I go back up here, and it actually told us a snapshot. It said when the depth, so the depth is the same thing as the height, is equal to 6 centimeters deep. So our snapshot is we know that height is equal to 6 centimeters. Well, this is the height, and this is the relationship for height. So I'm going to say 6 is equal to 3r, divide both sides by 3, divide by 3. We're going to find out that r is equal to 2. So I can come back here and say, all right, the snapshot for this particular thing is 2 squared dr by dt. Okay, so we're going to do some simplification. So negative 5 equals, and what we're going to have is 2 squared is 4 times 3 is 12. So we're going to have 12 pi times dr by dt. Divide both sides by 12 pi, divide by 12 pi. Those are going to go away. And then we can say, oh, all right, then dr by dt is equal to negative 5 over 12 pi. And that was centimeters per minute. So we need to have a proper concluding statement, so they would say, therefore, well, we're not quite done yet, I guess, because this is what the rate of change of the radius is. And we need what the rate of change of the diameter is. So we're going to reach back up to that other expression that we had. We had that dd by dt is equal to 2 times dr by dt. So it's going to be 2 times, and I know dr by dt is negative 5 over 12 pi. So that would simplify to be negative 5 over 6 pi. So there is dd by dt. So we can simplify, and we can, you could get a decimal for this, but I'm always happy for you to give me exact answers. So it's negative, and the negative is important because I need to choose the appropriate phrasing. So we would say the diameter is decreasing. Decreasing, again, because of that negative. So decreasing at, but we can state now, because we've taken care of the negative by saying decreasing, at 5 by 6 pi centimeters per minute. Okay, and there it is with a little bit of off the beaten path way to solve that one. So let's try another one here. How about we had the following scenario? We have a ship, and it is, a lovely ship. Okay, so it's a ship, and it sprung a leak, and it is sadly leaking oil, and the oil slick is getting bigger and bigger and bigger. That looks like a happy face, but I promise you, it's a ship. There's a fish, so we know it's a ship. So it's got an oil slick that's leaking. Now, this oil slick is going to be cylindrical in shape. So the depth of an oil slick is always, let's make it 5 millimeters. So regardless of how wide the oil slick is, it's going to be basically a disc. It's going to be a cylinder, a really narrow cylinder, or a really shallow cylinder that's only 5 millimeters tall. Okay, and I'm going to tell you, we'll keep the units nice for this particular one. I'm going to say that how about oil is leaking out of the ship at a rate of, well, just a tiny little ship. How about 2 liters per hour? Let's kick up the difficulty of this one a little bit. How about after 10 hours, how is the area of the circle as viewed from above changing? Okay, so here's the thing. So if we think about this oil slick, it is vaguely cylindrical, a very, very, very narrow cylinder, right? So we got this really narrow cylinder, and we know the height of this cylinder is 5 millimeters. Well, I know 5 millimeters is 0.5 centimeters. So the height of this thing is 0.5 centimeters. And it says that we're leaking at 2 liters per hour. So I would give you a conversion. I would say that 1 liter is equal to 1,000 cubic centimeters. Okay, so I'm going to convert everything into centimeters for this. I would also tell you some formulas. I would tell you that the volume of a cylinder, although again you should know this, is pi r squared h. Okay, so let's think about our givens. So we are given that dV by dt is equal to 2,000 centimeters cubed per hour. We're given our formula. We are given that the height is equal to 0.5 centimeters. And what we want, so what I'm asking for here is I want to know how is the area of the circle as viewed from above changing. So what I'm after here, I have no idea what this color is, but let's take this color. What I want to know is this circle, if you were, on a hang glider over top of this oil slick, and you were looking straight down at it, it would just look like a circle of oil. I would like to know at what rate is the area of this circle changing. So that's a little bit tougher. So we want, I'm going to just say dA by dt. Okay, so if you think you can get this, go ahead, pause the video now and give it a whirl. And if you're not quite sure, watch along. So here we go. Now, I've got a dV by dt. I want a dA by dt. But it's going to be pretty hard to rearrange this in terms of A. So this is where some experience and some practice, we're going to have an intermediate step. Okay, and the intermediate is going to be, we want to solve for dr by dt. And why we want dr by dt is because if we think about the area of a circle, we know that it is pi r squared, just straight up pi r squared. So if we know what dr by dt was, we could substitute it into this after we differentiate that. So if I think about that, if I differentiate this expression for a circle, we know that dA by dt would be 2 pi r dr by dt. So if we know what dr by dt is, we can relatively easily find out what dA by dt is. So what's interesting, and again, we're always going to cast our mind at this particular time to decide, are any of these values static or are they all dynamic? Well, clearly the radius and the diameter, they're going to be dynamic. As more oil pours out of this tiny ship, this is going to get wider in diameter. However, we have said that the height is always 0.5. So this one here is going to be static, right? Oh, I didn't pick the color, I just went over there. Okay, nevertheless, this is static. And it's really important to recognize that because that means I can substitute 0.5 into this expression right now. So I can say, that means that really my formula in this case is volume is going to be pi r squared times a half, or 0.5. So it is pi by 2 r squared. Okay, So that is what the actual expression is, because I was able to substitute the static 0.5 for the height in for the height and simplify it a little bit. So there's my volume expression. So I can differentiate this now. So if I differentiate this, we know that dV by dt is going to be pi r dr by dt. And I know what dV by dt is. It was actually given to us. dV by dt is 2,000. So I can put in that 2,000 pi. I'm looking for dr by dt. I don't yet have r. However, there's enough information in this problem to solve for r, because it says oil has been leaking out of the ship at 2 liters per hour after 10 hours. So that means we know the volume of this cylinder has to be 2 times, or 2,000, excuse me, times 10. So I know the snapshot volume. So that's kind of another given. It wasn't obvious to us right at the time, but we actually know what the snapshot volume is. We know that the snapshot volume is going to be equal to 10 hours times 2,000 per hour. So it is 20,000 centimeters cubed. Well, how's that useful? Well, we know the volume of a cylinder. Well, the volume is equal to pi r squared h. Well, I know what the volume of this cylinder is. It's 20,000. So there's 20,000. And pi, I don't know the radius. That's what I'm after. So r squared. But I do know the height, because the height is static. So 0.5. So I'm going to multiply both sides by 2 to get rid of that 0.5. So multiply by 2. So that's going to be 40,000 is equal to pi r squared. I'm going to divide both sides by pi, divide by pi. Those are going to go away. And then I'm going to root both sides. I'm going to root both sides. And I'm going to find out that r is equal to whatever 40,000 divided by pi square rooted is. I'm going to grab my calculator, because that's a little bit out of my scope. So I'm going to say, what is the square root of 40,000? So 4, 1, 2, 3, 4, 40,000 divided by pi. Okay. So it turns out that the radius of this particular slick is only, it's still big, 112 point, what was that? 112.84 centimeters. Okay, so there's my radius. And that's my snapshot radius. So that is what's going to go in there. So 112.84. So I'm going to divide both sides now by 112.84 pi. I'm going to divide by 112.84 pi. Those are going to go away, and we're going to find out that dr by dt is going to be equal to, and I'm going to have to grab a calculator for that as well. So we're going to have 2,000 divided by bracket, I'm going to grab that last answer that I had there, times pi. Type that in, and we're going to find out that the radius at that particular time is changing at, okay, so dr, where'd you go? There you are. Dr by dt is 5.64. So 5.64 centimeters per, I guess it was hour, correct? Yeah, hour. Now, there is my intermediate step. This is a big problem. We're not quite done yet. So we're going to take this expression that we solved for up here, because we really want dA by dt. And we're going to say, all right, well, that means that dA by dt is going to be equal to 2 pi, and I know what my r is. I already solved for it, 112.84 times dr by dt, which is 5.64. So I'm going to drop that all into my calculator, right? So I'm going to grab my calculator here. We're going to do 2 times pi times 112.84 times 5.64. And we're going to find out that I didn't type it in properly. What did I miss? I didn't put a bracket anywhere, so I don't need to close a bracket. And there we go. We're going to find out that that is increasing at, so dA by dt is 3998.73. 3998.73. So that is dA by dt, and that's going to be in centimeters squared per hour. Okay, so what we need to do here is we need to then take and we need to write a concluding statement. So therefore, the area of the top of the slick is increasing at 3,998.73 centimeters squared per hour. Okay, and there it is. Okay, so there are a couple of great problems. I will put up a few more practice problems for you to work on, and our next lesson is going to be involving related rates and shadows, and that's a pretty involved lesson.